Okay, let me start by thanking the organizers for this invitation. So I want to talk about some work that I did recently with my PhD student, two of my PhD students, Anish and Rupak, and with a postdoc, Rohit Ashwa, all in TIFR, and with a former student, Mrinal, who is now a postdoc in Heidelberg. So this is the theory part, and then we have a part, which was motivated by some experiments done by Puneet Paramananda from IIT Bombay. So I'll try to touch upon both these issues, and these are the references. Okay, so the main question that we want to address is the following, that suppose you take a many-body interacting system that shows a phase transition between an ordered and a disordered phase, and suppose you are in a regime in which the system doesn't like to order on its own. And in that regime, the question that we ask is, can we induce order in the system by kind of minimally tweaking the dynamics in a way that I'll tell you, how to do it. Of course, I mean, this is a very, daunting question. So, of course, we'll try to answer it in a particular context. But I hope the question is clear that you have a system that shows an order disorder transition, and I am in a parameter regime in which the system doesn't like to order, and how I can induce order in the system by tweaking the dynamics. So the particular setting that I would be looking at, I think nobody before me, unlike others, I'm not that lucky, so nobody has talked about this setup. So, or perhaps I am that lucky, and that is the setup of synchronization. So, what is this synchronization? So, it's a ubiquitous phenomenon that one observes in nature. So, it's the following thing, that you have a large number of interacting units, and each one of them has a dynamics that lets it settle into a stable limit cycle. Okay, for example, in this problem of metronomes which are put on a common platform, each metronome has its own stable limit cycle characterized by a certain frequency of oscillation, and I put a lot of them on a common platform, so there's some weak interaction between them. And the question is that, I mean, does this conglomerate settle into a globally synchronized phase, a phase in which all the metronomes are oscillating at a common frequency? And examples range from cardiac pacemaker cells and people clapping and power grids and so on. So the minimal model that has been introduced quite some time ago to study this kind of phenomenon goes by the name of the Kuramoto model. So the model involves limit cycle oscillators. Of course, you have many limit cycle oscillators, each one characterized by its own frequency of oscillation. And there are n of them, they are globally coupled. Everybody is talking to everyone else. So to characterize any such limit cycle, you need a phase. So theta is the phase, and this is the equation of motion of the system. These are nonlinear oscillators, and the dynamics is, it's that of a nonlinear dynamical system. So the first term on the right describes the inherent tendency of the ith oscillator to oscillate at its own frequency. But then the second term is due to interaction between the oscillators that tries to bring about global synchrony in the system. And these frequencies, these are quench disordered random variables, in the sense that each oscillator has got its own frequency of oscillation that doesn't change as a function of time, while this interaction, what it tries to do is to bring about global synchrony among the phases of the oscillators. These frequencies are they're so-called natural frequencies taken from some distribution, could be a bimodal or a unimodal distribution. And this system has been studied extensively, and what has been shown by many people is that if you are in the limit of a large number of such oscillators and you wait for long enough time, then the system goes into a stationary state in which it shows a phase transition, or more precisely a bifurcation between a synchronized phase and a non-synchronized or an incoherent phase. So here is the order parameter. The order parameter just gives an idea of the fraction of the oscillator phases that are synchronized. And when I plot this order parameter as a function of the coupling strength K is the coupling here, you see that there is a transition from an incoherent to a synchronized phase across a critical coupling Kc that can be derived exactly, and it has this particular form. So this is old stuff, and by the way, this is a snapshot of the system, the phases of the oscillators. Each dot here represents a phase, and being a phase, I mean, it can be represented on a circle, unit circle. So this is a phase in, this is the case in which the phases are completely unsynchronized. This is supposed to be a video, but it's not running anyways. And this is the case in which you have a macroscopic order in the system, a large number of phases are synchronized, and this is at the critical coupling. Okay, so this is the the order parameter as a function of k, and I come back to the question that I started out with, namely that can I induce order in the system, namely that can I modify the dynamics in a simple manner so that when I am at k less than kc, when the system doesn't like to order, I can induce somehow order in the system. And of course, I mean, the answer is yes, we can do it. And so there are two distinct mechanisms in which this can be done. One is the so-called stochastic shuffling, which was motivated by the experiments done by Puneet at IIT Bombay. And the second one is the so-called subsystem resetting. I'll talk about both. And the thing is that it doesn't require any external potential. You don't have to introduce an external potential, and you don't have to manipulate all the degrees of freedom. So there are n of them, and you may think that I need to do something for the whole set of degrees of freedom, but then I need to manipulate only a few. How few, I'll mention as I go along. So the rest of the talk, I'll talk about what are these protocols and how do they work and so on. Yes. Okay, so let's come to stochastic shuffling first. Okay, so here is a circle. So what I've done is that I have represented the phases of the oscillators by a dot. And remember that I have many oscillators, n of them in fact, and every oscillator has got a characteristic frequency associated with it. Okay, and these are quench disordered random variables. So every oscillator has got its own frequency. So what I've done is that I've represented the characteristic frequency of the different oscillators by a color, by a different color. For example, here is one oscillator, here is one, and so on. Okay, and they can go past each other. I mean, there's nothing that there's no exclusion, interaction, or anything. There's no lattice, so they can go past each other. So what I do is that I start with a given initial condition. Okay, so this is one oscillator with this frequency and another and so on, and this is my time direction. Now in the original Kuramoto model, every oscillator would retain its frequency, that is to say in my language would retain its color. If I am red, and in fact I am red, I will continue to remain red. Okay, I mean, I am not red, my pullover is red. Okay, but this is the time direction. Then what I do is that I let the system evolve with this initial condition for a random time, and I then shuffle the frequencies. That is to say, I shuffle the colors. I am red, and at this instant I become blue, and a red colored particle becomes blue, and a blue colored particle becomes red, and so on. Okay. And then I do it at this random time, and then I let the system evolve for another random interval, and then again I shuffle the frequencies. That is to say that I shuffle the frequencies among the oscillators at random intervals taken from a Poissonian distribution, from an exponential distribution. Okay, so these variables, that the frequencies which were quench disordered in the original setting are quench disordered in this modified setting, but only for a certain random interval, after which they change their there's some shuffling that is done, and so therefore I mean the frequencies are always taken from the same parent distribution. It's just that who is red and who is blue, that is who is moving with 5 Hertz and who is moving with 6 Hertz, that information gets changed. One thing you notice that at the instance when I shuffle the colors among the oscillators, I don't change their relative position on the circle. That is to say that when I'm shuffling the frequencies among the different oscillators, I do not update the phases of the oscillators. So therefore the phases of the oscillators retain their information, the full history of time evolution. That I don't do anything, I don't play with. I just change the frequencies among the different oscillators. So that's the protocol of stochastic shuffling. While in the case of stochastic resetting, subsystem resetting, what I do is that again I have these oscillators with different colors. Here there is no shuffling. So here if somebody is red, he continues to remain red. There is no shuffling. The frequencies are really quench disordered in time. But what I do is that I choose a subset of the oscillators. For example, here I have chosen these oscillators, the ones which are circled here, 1, 2, 3, 4, these four oscillators. I have chosen a subset of these oscillators. What I do is that I start from this initial condition, I let the system evolve, and then at a random instant, I reset the phases of this subset, chosen subset of oscillators to their initial values. And I keep doing it. Okay. So I have n oscillators. Let's say I choose oscillator number 5, 17, 56 and 89. And well, I start from an initial condition, I let the system evolve, and at a random instant for this chosen subset of oscillators, 5, 16, 7, I forgot what are the numbers that I mentioned, I reset their phases to their initial values, and I keep doing it. And I reset them at random times taken from an exponential distribution. I think nobody has talked about stochastic resetting. That's what I gathered from the program. So this stochastic resetting is a recurring theme in current day research, and I guess there are many people in this audience who have worked on stochastic resetting, starting with Satya. And so, this is an ode to resetting. You may read it, later. There's a review that you may look up, and this stochastic resetting, in fact, it appears in a variety of dynamical systems, and it has, emerged as an interesting theme to generate non-trivial, non-equilibrium stationary states, and so on and so forth. Okay. So coming back to stochastic shuffling and stochastic resetting, see, the new thing that we are introducing here is that in all earlier work, whenever people talked about this stochastic resetting, what people have done is that you have the whole bunch of degrees of freedom. You start from an initial condition, you let the system evolve for a random time, and then when you reset all the degrees of freedom to their initial values. Here I don't do that. I reset only a chosen subset of the degrees of freedom to their initial values, and I keep doing it. And as you will see, this leads to interesting consequences on the steady state features as well as on the dynamical aspects of it. So let's first come to stochastic shuffling. Shuffling, you remember what I did was I let the frequencies be shuffled among themselves after a random time, and I keep doing it. Okay. And our aim was the following, that I am at a parameter regime in which the system doesn't like to order on its own. And the question is, can I induce order in the system by doing this shuffling? More precisely, I want to know that in the Baire model, there is a critical coupling above which the system orders. Can I reduce the critical coupling? And that would mean that I should be able to achieve synchrony in the system. And indeed, that is what is happening, that here I am plotting the phase diagram in the k lambda plane. K is the coupling parameter. It just tells you how strongly the different oscillators are coupled, and lambda is the rate at which I am doing the resetting, shuffling. That is to say, 1 by lambda is the average time between two shuffling events. And as lambda goes to 0, that is when I go back to the Baire model, then I see that there is a critical coupling Kc above which the system synchronizes. But then when I jack up lambda, this shuffling rate, then I see that indeed this critical coupling, it reduces, and it in fact approaches a small value, approaches 0, close to 0 as lambda goes to infinity. Okay. So indeed, I am able to achieve synchrony in the system, reduce the critical coupling by introducing this protocol of stochastic shuffling. So that is for shuffling, for this shuffling protocol. And this is what happens when you do subsystem resetting. Let me just remind you that subsystem resetting is what you do. You don't shuffle. The frequencies are what they are. You choose them at t equal to 0, and they are quench disordered. They remain unchanged in time, but what I do is that I choose a subset of oscillators and I keep resetting their phases to their initial values at random instances. And this is again the phase diagram. So here K is the critical coupling, and what is F? F is the fraction of the total number of oscillators that constitute my system that I am resetting. That is the subsystem which is subject to resetting. And as you can see, I mean, the color coding, it just gives you an idea of how strongly the system is synchronized. And as you can see that, this is for, two particular situations. Okay, maybe we can look at this situation, which is more interesting of the two, which is this is K and this is F. And as you can see that as F increases, that is as you are resetting more and more, as you increase the number of subsystem oscillators, the system is getting synchronized. But that is not all. It turns out that when you introduce this subsystem resetting, there is a particular parameter regime in which the system doesn't have any stationary state. I mean, that is quite interesting because in the original model, the system always had a stationary state. And just by introducing this protocol of subsystem resetting, I'm able to introduce a dynamical phase transition in the sense that as I, at this particular K, increase the fraction of the oscillators that are being reset, I go from a non-stationary regime to a stationary regime. Okay, so I have about 8 minutes left. So let me give you an idea of the the kind of analysis that one does, but maybe not for both the setting, but just for one, namely this subsystem resetting. So in this subsystem resetting, I mean, I'm flashing this same slide again. Namely, what you do is that at random instances, you choose a subset of oscillators and reset their phase values to their initial value without doing anything with their frequencies. Okay, and we would like to understand analytically how one goes about studying this.
The initial values are all the same, is it?
Sorry.
In the reset to the initial values, the initial phase is all the same.
It could be anything. I mean, whatever you choose, I mean, you may choose them to be same, and so when you reset, you bring them to the same value, or they could be different also. Okay. So what you do is that basically the kind of analysis that you would do. Okay, by the way, so this is a snapshot of the time evolution of the order parameter of the system. Okay, so this is the bare model. So remember, my coupling is smaller than the critical coupling. So the order parameter as a function of time would decay to 0 because the system on its own would not like to show any order. Here I show the order parameter of the reset subsystem, the part of the system that is being subject to resetting. As you can see, I start from a fully ordered phase, and on its own it would like to get disordered and therefore it decays. But then at this instant there is an instance of resetting, and therefore it goes again to 1 and so on. So this is for the reset subsystem, and the question is what happens to the non-reset part of it, the complementary part of it. And this is what I show here, that the complementary part, I mean the order parameter doesn't decay all the way to 0, but then it decays to a non-zero value. It just shows that the whole system is getting synchronized, although I am playing with only a part of it. Okay? So the kind of analysis that one would like to do has to, okay, first of all, we write down the equation of motion. I mean, a simpler case to study is when you are resetting all the time. That is the case of infinite resetting rate. In this case, I mean, this was the original equation, and since I am resetting only a part of it and I am resetting it all the time, therefore you may think of this resetting part to have degrees of freedom whose values are frozen in time. So that introduces in the non-reset part of the system an effective on-site field, which is like this. And so you can write down the equation of motion for the non-reset part of the system in this manner. So this part is coming due to interactions between the oscillators of the non-reset subsystem, and this the second term here tells you how the non-reset oscillators are being impacted by the resetting that is being done in the reset part of the system. Okay, so this is the equation of motion, but the problem is that, it's not a Hamiltonian system and there's no noise and there are no, Langevin or Fokker-Planck equations to study. So what one does is that one introduces, of course, a probability distribution, because we are interested in the large, in the limit of large number of oscillators, and write down some continuity equation. But then the rest of it becomes very difficult to study, because you don't know how to solve this continuity equation. So we use some earlier results derived by Oth and Antonsen, utilizing the integrable property of this system to derive a closed form equation for the order parameter of the non-reset subsystem. Okay, so the details I'll just skip. Sorry, I did not have time to prepare a short talk. I ended up preparing a long one, but the slides are on the website, so you may have a look as to how these things are done. And it turns out that in almost all cases that we looked at least in the Kuramoto setting, we were able to solve analytically for the order parameter of the non-reset subsystem for both infinite as well as finite resetting rate. Of course, when the resetting rate is infinite, there's a clear time scale separation. There's a time scale at which you are resetting, and there's a time scale corresponding to the bare evolution of the model. And if the two are well separated, then one can solve rather straightforwardly. But even when there is no time scale separation, it turns out that one can make use of certain features of the dynamics, integrable features of the dynamics, to obtain closed form solution for the order parameters of the non-reset subsystem. So let me just jump to my conclusion. Indeed, yeah. So this is the main conclusion, that the question that I started out with was, I have a many-body interacting system that shows an order to disorder transition. I am in a parameter regime in which the system doesn't like to order, and can I induce order in the system by doing something? And that something turns out to be either stochastic shuffling, which I mentioned was motivated by experiments with Wheatstone bridges. Not apparently, it was evidently true that for experimentalists it was quite easy to shuffle frequencies by changing the resistances in a Wheatstone bridge network. And that's how, we first had the experimental results. Puneet told me about these experiments, and then he was wondering if there is a way to understand it. And so this is the stochastic shuffling, and what it does is that it is able to reduce the value of the critical coupling to observe order in the system. As you jack up the resetting rate, the critical coupling decreases. And the second one is this stochastic subsystem resetting, in which you have a macroscopic system and you manipulate the degrees of freedom of a part of it, and you see how does it impact the rest of the system. And it turns out that in this case you can induce order in the system, but also it is not always true that you will have a stationary state in the system. You may end up being in a parameter regime in which the system doesn't show any stationarity. So I just end with this last thing. So we also did it for spin systems, classical spin systems, the so-called blue memory Griffiths model, which involves this spin one, particles which are interacting all to all. There's an all to all interaction and there's an on-site interaction. So this is the phase diagram of the model, the bare model. K is the coupling, K is the on-site strength, field strength here. And what the system shows is a tricritical point connecting a line of first order and a second order phase transition. Okay, so this is for the bare model. So you take this model, and the system is in canonical equilibrium, and you ask what is the phase diagram of the model in the KT plane, and this is what you get. You get a line of second order phase transition and a line of first order phase transition. And now the question that we ask is, experimentally it is not quite easy to tune the coupling parameter. So can I reproduce this full phase diagram by keeping the coupling constant K fixed, but by just playing with the fraction of the spins that I am subjecting to stochastic resetting, subsystem resetting. And indeed, it turns out that, of course, we have some preliminary, I'm showing some preliminary results here. For example, this one, if you choose appropriately the configuration to which you are resetting, then you are able to reproduce the full phase diagram as shown here by just tuning the fraction of spins that you are resetting. Okay, so I think I'm out of time. So that's all I have to say, and there are more things to do. For example, in quantum systems, how does subsystem resetting lead to interesting results, etc. Okay, thank you.
Thank you.
So instead of this reshuffling, if you redraw the frequency, will it work or not?
Yeah, it will work. I mean, if you have a large number, if n is very large, if you have a very large number of oscillators, which is the case that I am doing, then it's basically the same, that you redraw, but then since you are drawing from the same parent distribution and you have many oscillators, so it's as good as shuffling. In fact, in simulations, we were doing redrawing basically.
Each time you choose a new fraction?
No.
You always
The same set, 1, 5, 7, 8. So same set, same number.
And what happens if you choose?
Well, then it averages out, yeah, and then it doesn't work really. So it's like, I have a big system and I've chosen to subject only a part of it, this part, to something, and I see how does it impact the rest.
And when you say that there is no stationary state, it means that it doesn't synchronize? Or?
Yeah, the order parameter goes into a time periodic state.
Okay,
I mean, it
so
doesn't go to a time independent value. Yeah.
So if you reset, the same question as Sriram, like if you reset to the same value,
yes,
then it looks like you are favoring synchronization. But if I reset to, let's say, randomly, the initial condition was random,
yeah,
then it should favor sort of desynchronization, right? I mean,
no. So the question, what matters is what is the fraction that you are resetting. Okay,
some fraction.
Huh.
But if you reset them, like if the initial condition was they all started at the same phase,
yeah,
and you reset to that, that would favor synchronization, right? I would
yeah, of course. I mean, the amount of synchrony that you induce in the rest of the system, that will depend on the value to which you are resetting.
Right, yeah.
Of course, that will be different. But what happens is that when you have synchrony in the system, I mean, when you induce order in the system, it is always synchronized. I mean, the amount of order may vary depending on whether you are resetting to a completely disordered configuration or a partially disordered configuration, but it is always ordered.
If you reset to a completely disordered one, it should disorder.
No, because the rest of the system, I'm averaging over initial conditions, and the rest of the system is trying to order. So therefore, the competition, in the competition, one part wins over. So in the case of infinitesimal amount of resetting, also it works. Like if you reset only a very small, tiny fraction of the total number of oscillators, still it works, simply because you are not resetting the whole of it. I mean, there's a part that you are resetting.
Last question.
About the experiment, I mean, what was the experiment?
Okay, so in the
experiment, why did they do the experiment?
Okay, I think why they did it was, okay, they had a Wheatstone Bridge network in which I hope everyone is familiar with Wheatstone Bridge, at least from college days, I guess. So what they did was, okay, there are this, the keys that you put in to change the resistances. And what they were doing was that they were just changing them randomly to see, I don't know why did they do that particular thing, but then that's what they were doing. I mean, probably a game to play with. And what they found is that, in the case of Wheatstone Bridge circuit, I mean, there's this thing of oscillations. I mean, you look at the current profile, and they found that it does show, you don't have to change as much as you would think one would need to.
Okay, so thank you, Shamik, and thank you to all the speakers of this second session.